Another special effect pigment is a pearlescent pigment, where regular reflection takes place on a highly refractive, highly parallel pigment platelets, such as titanium dioxide on mica. They actually deposit a thin layer of titanium dioxide on mica platelets. They get special effect colors. This is how the light bounces off of it. Aluminum flakes are oriented within a vehicle, so you want them to line up in a certain direction so that the light bounces off of it in a certain direction. The way the light hits it, the flat surfaces reflect the light in one way, the edge of the flake reflects light in a different way. That different type of reflection can result in different type of effect of the color. And again, you could spend hours and hours explaining this, physics, but I imagine you probably don't want to do that. Here is some chips that we made in the lab, a special effect colorant where it actually has color travel. Depending the direction you're looking at it, it will change color. And I don't know how well this will show up here. This is one color of that type of colorant. There's another one. The first one is called copper, I think. This is jade. I believe this one is sapphire. If you look kind of at this one here, that looks greener, I would think, me anyway, and this looks bluer. They're all the same chips, all the same color, but slightly different angle you're looking at it gives it a different color. These pigments are starting to get popular, especially in automotive paints. When we were working with these pigments, they were on our way to a show in Detroit with a Harley motorcycle that was painted with this type of color. This colorant is very expensive. This type of pigment will run about $400 to $500 a pound. It's pretty expensive. These pearlescent pigment types can demonstrate color travel, give you a really bright white color. We have a barrel of white pearlescent pigment in the lab, and we mix it with other colors, and we can make a lot of different colors of pearlescent that we use for some of our cups. Maybe transparent. Phase interference with white light causes the effect, has variable particle size. Disadvantages: they can be translucent and transparent if you don't want that. Those chips I showed you have a little bit of black in them, a little bit of carbon black. If we just put the colorant itself in the resin, it would look kind of translucent white, a little sparkly, but you wouldn't get the full effect that way. You've got to have a little black in it. Difficult to disperse properly. You've got to get them lined up in the right direction. They work easier in paints where you control that better than they do in plastics. Variable chemical resistance and light fastness, heat stability, depending on the particular colorant. Very high cost per weight, and has variable particle size. Interference colorants. The optical effect of colored luster pigments is caused wholly or mainly by the interference of light wavelengths by a multi-layer structure, such as iron oxide layers on mica. Again, a platelet type material. What's interesting about this type of color, the color that you get is completely related to the thickness of our pigment particle or pigment platelet. All of these colors that come off of here, the white, yellow, red, blue, green, all have this exact same chemical makeup to it. The only difference is the thickness of the plate. And here shows what those thicknesses are. And because of that interference of the wavelengths of light, you have canceling out of some wavelengths, adding of other wavelengths, so you get the different colors that you get from it. The chemical makeup of these type of colorants are the same for all the colorants. The difference is the thickness of the platelet. Interference pigment properties: high refractive index, non-toxic, chemical resistant, brittle particle, good light fastness, heat resistance, flake-like particles, can exhibit color travel. They have variable opacity. The advantages of those properties: can have color travel if you want that. Bright colors, wide range of hues, just need to change the different thicknesses or the thickness of the particles. May be transparent, to selectively absorb certain colors. Again, variable particle size. Disadvantages there: high cost per weight, variable resistance. Again, difficult to disperse properly, to get them lined up in the right direction so you get the effect that you want. Harder in plastics than in paint. The more special effect colorants, these are called luminescent colorants. First one is one you're probably familiar with, fluorescent pigments. The optical effect is the result of the ability to absorb radiation and to immediately emit it as a visible light of a longer wavelength. We'll see a graph in a second that shows it takes energy from the ultraviolet region of the spectrum, shifts it over to the visible part of the spectrum. That's what makes it look brighter than bright. Gives you that fluorescent effect. Phosphorescent colorants have the optical effect, the result of the ability to absorb radiation and to emit it as visible light of a longer wavelength over a period of time. So this is the type of colorant that you put in the light, let it absorb light, and then you could take it in the dark and it keeps emitting light. So that's the glow-in-the-dark kind of thing. My daughter has glow-in-the-dark stars on her ceiling. The light's on, it absorbs the light, you turn the light off, and then the stars glow for a certain amount of time, and then they dissipate and they don't have any more energy left. So the difference between the two is the fluorescent pigments do it immediately, and the phosphorescent ones do it over time. Here's a graph that shows how a fluorescent pigment works. What it does is, this would be the curve, this yellow one here, without that fluorescent part to it, and that's what the color would look like. When you add the fluorescence to it, it takes the energy from this part. 400, remember, is the beginning of the visual spectrum. It takes this energy from the ultraviolet, re-emits it in the visible. So this is the fluorescent effect, and this blue curve gets added on top of this yellow curve. So then we have this darker blue one there as our total, adding those two together. What you can have, if you look at this number here, 1, you actually can have more light reflected off of a surface than actually falls on it in a certain wavelength. You can't do it all the way across. You can actually get more than 100% reflectance. And that's what causes that fluorescent effect that we see in like hunters' apparel, really stylish looking orange hats that hunters wear. That's where that effect comes from. A little hard to see in this one. I tried to take a picture. This is a cup that we put some fluorescent colorants in. You can see there a little bit of the effect. I think I have one more. Yeah, this one shows a lot better. That's actually a dark, pretty much black room with no lights in it, and the only light present for this picture comes from the actual fluorescent pigment. See, there's a yellow there. That's the brightest, kind of a orange, and this is kind of a, it's actually kind of a pink. Those are a fluorescent effect there. Fluorescent pigment properties, it gives us very intense colors, ultraviolet functional, so it's the UV light that causes it to really stand out. If you go into a place that has a UV light, for instance, you look at your clothes and the whites really jump out. That's because whites sometimes will have optical brighteners put into them, which have UV colors in it. Some laundry detergent. One commercial way back when they used to say, they'll make your whites whiter than white. They're actually putting either fluorescent pigments in it that help brighten it, or actually a blue pigment in it that counteracts the yellow that whites tend to turn yellow. Yellow and blue get it back to white. These fluorescent pigments may bleed. They're usually based on dyes, even if they're in a pigment form. Low bulk density, usually transparent, emit visible light, fair heat stability, not great, difficult to measure the effect, especially if you want to use an instrument. So generally, if you're matching with these, you do it visually. Advantages: bright colors in a wide range of hues, translucent, transparent, selectively absorb, pretty high tinctorial strength, they're pretty strong, high visibility. They do need ultraviolet light to activate. If you're outside, they work pretty well because sunlight has ultraviolet light in it. And even inside, there's some ultraviolet components to these lights. Disadvantages: may bleed. variable chemical resistance, light, fast, and heat resistance depending on the particular material, and again needs ultraviolet light for that effect to show up. Some other colorants that you may not think of or be aware of: chemiluminescent colors. The optical effect is a result of a chemical reaction that produces visible light as part of the reaction. Can you think of any product that you might use that uses this type of colorant in it? About those glow sticks that you crack. What it is there's a tube in there that has one chemical on the inside, and then you crack that inside layer, it mixes with the other chemical, and it gives off light. And that's chemiluminescent colorant. Luminescent color. At a couple of last retexts we went to, one of the pigment suppliers make this, and they had cups that were hollow, and you cracked them and the cup glowed. Lasted a pretty long time, too. They were kind of a one-time shot. Bioluminescence colors. The optical effect is produced by biological mechanisms within living plants and animals. There are some animals that actually produce their own lights. Animal shows, and you show about deep-sea animals. You'll see that since there's no light that gets down to the bottom of the ocean, they have to produce their own. And it's really kind of interesting. Thermochromatic colors. Optical effect is a result of the ability to become chromatic or change hue as the temperature of a colorant changes. I think where we use that. Those little thermometers, thin thermometers you stick on the side of the aquarium, and the color of the strip tells you what the temperature is. Photochromatic colorants. Optical effect is a result of the ability to become chromatic or change hue as the incident radiation changes. As you expose it to more light, it changes color. Take the light away, it changes color. Some toys are using these concepts for changing colors, dolls with different color hair and that sort of thing. Piezo-luminescent colors. Optical effect is the emission of visible light when pressure is applied. So you put a force on it, and it actually produces light, changes the pressure of that energy into visible light. Hydrochromatic colorants. Optical effects is the development of or a color change when exposed or removed from the presence of moisture. So it can be used to tell how much humidity is present, for instance, or how much moisture is present in something. Bob Charvat has been working on a project that's something like this. It's irreversible, though, if I talked about it in this class, with golf balls. I mentioned this golf ball project. Here's the other class, where golf ball manufacturers want the golf balls to change color if you hit them in the water, so golf courses don't fish them out of there and sell them as new. So, if they're white golf balls, you dump them in the lake, they pick them up, and then they try to sell them. They're no longer white anymore, they're a different color. And that change that changed it to a different color is permanent. A lot of these pigments, it'll go back and forth depending on the moisture content. Classification of colorants. We use something called the color index to identify colorants generically. Pigment suppliers have their own names for the colorant, trade names, that sort of thing, but we have a generic color index. We can use a term or a name like phthalocyanine blue. That's a color index name. And also a number that goes along with it. Another name for phthalocyanine blue is pigment blue 15:1. There's actually 15:2, 3, 4. Those are all phthalo blues, but they're all a little bit different chemically. And then there's also a 5-digit number that describes that particular colorant in more detail chemically. Now the color index has about 600 pigments listed and about 9,000 dyes. There's a lot more dyes, obviously, than pigments. And it provides some basic information about the chemical structure, method of application, fastness data, or stability data, names of manufacturers, and trade names for those particular colors. When you're trying to make a color match, you have to figure out which colorants to use, and it's probably the most difficult thing to do. You need to have information about colorants. Sources of information are experienced people you're working with, general colorant literature. We can have the color index, or the Modern Plastic Encyclopedia produces a reference sheet on colorants. Suppliers of colorants have a lot of information on the colorants. When we go to our retext, our conferences, the students come back with those kind of things that I passed around. Those came from the retext. The user's experience. So those are all ways of getting information about colorants that you want to use. First one is the color index, which is a standard reference published by the Society of Dyers and Colorists. Remember where we heard that before? The same group that came up with the CMC equation. Colorants classified by method of use, designated by a generic number. So like I mentioned, methylcyanine blue is referred to as CI pigment blue 15-1. And then also a 5-digit number that gives the chemical constitution of the colorant, if that's also known. Sometimes manufacturers don't want to give the chemical structure of it. Modern Plastics Encyclopedia is a reference book published by the industry magazine Modern Plastics. It has many sections that give technical data on many materials used in industry, and it has a good reference section on colorants. Here is an example of a shade card from Colorant, but it has an example of the actual color, what it looks like. This is the mass tone in a couple different white letdowns. It has other information about fastness, weathering, blooming, heat resistance, heat stability, and solvent resistance. There's some technical data about its properties and about its color. When you select a colorant to use, there's always a compromise between the hue, the chroma, and the lightness desired by the designer, what the processing properties of it are, and what you're going to process it in, which process like injection molding or blow molding. End use properties, where you're going to use that product once you produce it, outside, inside, chemical environment, and the cost of producing that color with the required properties. For the better properties, usually the higher the cost. Sometimes the customer doesn't want to pay the cost that it costs to actually do what he wants it to do. You have to be realistic in what you're trying to do. Some important colorant properties. When choosing colorants to use in a specific plastic for a specific application, the following issues must be considered. Is that colorant compatible with the resin? Some colorants can't go in certain resins. What's the light fastness requirement and the weatherability for the end use? How cost effective is that colorant? The amount you have to use versus what the cost is. Heat stability. How hot are you going to run your process to make your part? Will it bleed? And how hard or easy is it to disperse? Can you get it dispersed enough to make a good color with that particular colorant? Once you make your colorant that you're going to sell to processors that they're going to make parts out of, you can sell it to the processors in several different forms. And those forms are pellet color concentrates. They're pellets just like resin is, but they're concentrated color or other additives. Dry colorants are powders. Liquid colorants are obviously liquids. Multifunctional concentrates that have color plus UV stabilizers in it, heat stabilizers, other things. And then our master batch, which is the resin already colored with the colorant. Pellet color concentrates, we make this in our lab. Most common method for buying color. Colorants are pre-dispersed in a carrier resin compatible with the resin to be colored. Usually it melts at a little bit lower temperature than the resin you're coloring, and then has to be compatible so it doesn't give problems with that. Used at a predetermined letdown ratio. And what that means is if we have a letdown ratio of 25:1, that means that each unit of concentrate colors 25 units of plastic. If you were to color, for instance, or you want to color 100 pounds of resin, it would take 4 pounds of concentrate. For every 25 pounds, you need 1 pound of concentrate. So that's how you would figure out how much you would need. Dry colorants used mostly in processes that use powdered resins. The most common process for that is rotational molding. Colorants are sold in powdered form, and it's not just the pigment, but there's other additives that actually go in that so that it disperses correctly, and they're typically sold in unit bags. Units are sized to color a specific amount of plastic. So your unit bags may be one bag colors 100 pounds of plastic, or 1,000 pounds, or whatever you want it to be in. But one thing about the dry color, can be much dirtier than pellets, because if you spill dry color all over the floor, it stains a lot more than pellets do. Pellets, you can just sweep them up. Liquid colors, another form of colorant that can be a little messy, comes in a liquid form in buckets that looks kind of like a thick paint. The colorants are pre-dispersed in a liquid vehicle now instead of a plastic vehicle. Liquid is sold in pails or drums and typically pumped directly in the feed throat processing machine by means of a specialized metering pump. So you pump it right in at the feed throat. Typically allow for higher letdown ratios than the other forms of concentrate. You can have or less concentrate to color a given amount of material. You make higher letdown ratios. So instead of, say, a 25-to-1 for a pellet, you can make 100-to-1 letdown ratio. Multifunctional concentrates are concentrates of any form that contain not only colorants but also other additives part of its formula, such as lubricants, heat stabilizers, UV stabilizers, impact modifiers, things like that. The thing to be careful of is that while these are not colorants, they can affect the final color of your finished part, or take that into consideration. Master batch. In this form, no concentrate is used. The material is purchased by the processor, is pre-colored by the color supplier, and used directly by the processor. No measuring or mixing is required. Easier to use, but is the most expensive. You're buying a bunch of resin along with it.